So, in this reaction, which is very famously called as Haber's process, so before moving ahead, we are going to balance this equation. So, if we can see, the number of nitrogen atoms on the left hand side of equation are 2. So, we cannot change the subscript in a chemical equation. We can only put a suitable coefficient in front of the molecules, or it can be atoms, or it can be compounds. So we can only change the number in front of these molecules. But we are never going to change the subscripts over here. So if we need to have two nitrogen atoms on the right hand side of this equation, so we are going to add 2 over here. So on both sides, nitrogen atoms are 2. Now this 2 indicates 2 nitrogen atom, but when we are going to calculate the hydrogen atoms, you need to multiply this subscript along with the hydrogen into this coefficient. So this will be 3 into 2, 6 atoms of hydrogen. So if we need to make 6 atoms of hydrogen over here, we are going to put the opposite number over here, 3. So 3 into 2, 6, 3 into 2, 6. 6 atoms on both sides. So this is perfectly balanced equation. So next case, one more thing that I want to add over here is this equation. Though it's a chemical equation, but the state of matter on the left hand side of the equation and the right hand side is going to be is gaseous state. So all the molecules in this equation are in the gaseous state. So in a chemical reaction, we say that the state of matter must change, but it's not true in all the cases. In some cases, the state of matter remains the same, so it's not changing. Now, this is something called as a state of equilibrium. Equilibrium in detail we'll be discussing in the future lectures. So, this reversible sign that you see is indicating that there is some kind of equilibrium maintained. Just like if you see in that game Seesaw. So, just imagine two kids, they are just balancing at one particular state, they are not going up and down. So, that equilibrium they are going to maintain. So, at some point of time, the concentration, the amount of nitrogen and hydrogen, or you can say the concentrations are going to be equal to each other. So, as soon as ammonia is getting formed, nitrogen, hydrogen is getting consumed, they will chemically react. So, if we don't remove this ammonia from the reaction mixture, once it has formed, there is a possibility this ammonia can change back into nitrogen and hydrogen. That is the meaning of equilibrium. So it's a reversible process. So about equilibrium we'll be discussing in future lectures, but let's call this particular process as reversible. As I've told before, this sign is for reversible reactions. Though it's a chemical reaction, but it is a reversible change. Now moving ahead, I call this equation as a famous Haber's process. Now Haber's process, it's a commercial method for production of ammonia. So industrially, how do we produce ammonia? That is with the help of this equation. Now this might be very much complex when it comes to the practical terms industrially, but yes, this one equation is very much important for us. Now there are certain issues with this equation. So these issues are, if we use this equation at a low temperature, so I'm going to write what are the problems, like what solutions that we try to find it out, because manufacturing ammonia from nitrogen and hydrogen is not that easy task. It's difficult. because they both are in the gaseous state. We need to maintain the temperature, we need to maintain the pressure also. So, if we, for example, if we use high temperature, so let's say somewhere around 700 to 800 degrees Celsius, then rate of reaction is high. So, what's the rate of reaction over here? Rate of reaction meaning the speed of this reaction with respect to time is going to be high if we are using high temperature. But the yield of ammonia is low. That means the amount of ammonia that we require from the, you can say, set amount of nitrogen and hydrogen, the yield, we call it as a yield, that is quite low if we use high temperature. So rate of reaction, meaning the reaction is taking place quite fast. There are certain chemical reactions which might take hours, which might even take some longer hours, some, you can say, some seconds, some minutes. So it's going to take a lot of time. So if we are giving high temperature plus the ammonia yield is also low, that is one issue. Second, if we reduce the temperature, if we use low temperature comparatively to 700 to 800 degrees Celsius, then rate of reaction is low. That means the speed with respect to time is going to be very much slow, but the yield of ammonia is high. That is experimental observation that most of the scientists, Haber's process, that's the scientist name that they have observed. So what to do in this case? Now, low temperature, if we are giving, no doubt we are getting the yield of ammonia perfectly. But what about the time period? So, the rate of reaction is very low. So, the reaction is not speeding up, it is moving very much slowly. So, what we are going to do about it? We can't waste time like that. So, we need to make sure the reaction happens at a short span of time. Plus, it's also giving us good yield or good amount of ammonia. So we want both the things. So in this case, what we can use a catalyst. So catalyst is a substance. So catalyst can be anything. It can be atom, it can be a metal, it can be a compound, it can be anything. It's a chemical substance. So let's add, it's a chemical substance which alters. So I always use the term alters because we do have catalysts which are negative in the sense uh, decrease the rate of reaction. So which alters the rate of reaction without affecting the reactants and products, and without affecting itself. So it's like catalyst can be of many types. I'm just going to discuss only two over here in brief. So we have something called as positive catalyst, and then we have negative catalyst. So these are also called as poisons. So if you have heard about enzymes, which are working for so many metabolic pathways in our body. Those are something called as biocatalyst. They also catalyzed multiple metabolic pathways in our body, and that is naturally available in our bodies over here. So, but what about synthetic catalyst? What about catalysts that we can use in these kind of reactions where the rate of reaction is very low? So why we need high rate of reaction? Because at low temperature the rate of reaction is low. So how we can speed it up? By adding a catalyst, and to be more precise, the positive catalyst, because it's going to increase the rate of reaction. It is not going to change the concentration of reactants, it is not going to change the concentration of products, and it is not going to change itself. So the catalyst that we use over here is iron. In Haber's process, the positive catalyst that we use is iron. So this iron will make sure that the nitrogen and hydrogen they chemically react and they produce ammonia with high rate of reaction. So we will get ammonia in less time period compared to what we were doing with high temperature. So adding on, we are also reducing the temperature. So initially I wrote 700 to 800 degrees Celsius temperature, somewhere around this range. So after using the catalyst, we can use a temperature somewhere around 400 to 450 degrees Celsius, and with the atmospheric pressure of 200 atmosphere. So the temperature is also reduced. Now, do remember one thing, industrially, if we are using very much high temperature, it's an added expenditure for the industries. So why not go with the low temperature? Why not give low temperature to the same reaction by adding a catalyst? And that catalyst is not very much expensive. So why not go ahead with that? So benefits of using iron as a catalyst: rate of reaction has speeded up. It has increased. The reaction rate is increased now, and we are using the low temperature. So both benefits. And one more feature for this Haber's process that we use over here is something called as a promoter. So promoters are again chemical substances which increases the efficiency of the catalyst. Now we don't use promoter in most of the reactions, but yes, in Haber's process we are using a promoter, and the promoter name over here is molybdenum. So the promoter used in Haber's process is molybdenum. It's a metal. Symbol is Mo. So remember, positive catalyst is going to increase the rate of reaction without changing the concentration of reactants and products, without getting change itself, without affecting anything, without participating in the chemical reaction. So it increases the rate of reaction towards the forward side, towards the product side, so we can get good yield of product. And negative catalyst, they decreases the rate of reaction. So these examples we'll be taking later on. We'll be talking about different kind of catalyst also later on, but do remember about these. So it's a very important reaction in chemistry. Haber's process is a very famous process. So moving ahead, meantime we can take one more example for balancing. Iron reacting with steam. This is steam. Steam has to be in the gaseous state. This is in the solid state. And it is forming Fe3O4, which is in the solid state, and hydrogen gas. So Fe3O4 is also called as triiron tetroxide, or we even call it as ferroso ferric oxide, or we commonly call it as a mixed oxide of iron. So if we see in the later part the structure of Fe3O4, so still now we haven't done the chemical bonds, but after learning about the chemical bonds, we can actually figure it out, the structure of Fe3O4. So why do we call it as the mixed oxide of iron? Because it has both the charges, Fe plus 3, Fe plus 2, something we call it as oxidation number, that we will be learning later on. So let's try to balance this equation. So if we can see, iron over here are 3 atoms, so we can quickly put a coefficient in front of this iron, so it will be 3. And now always try to remember one thing: try to balance everything else but hydrogen and oxygen in the last, and keep oxygen in the last when it comes to balancing chemical reactions. So now over here we are going to balance. Hydrogen is already balanced over here, but we have our oxygen. Oxygen, we have only one atom on the left hand side in steam, and we have 4 oxygen atoms on the right hand side. So how we are going to balance it? So if we try to balance oxygen, let's put 4 over here. At least our oxygen is getting balanced in this part. So hydrogen is 4 into 2, 8 atoms of hydrogen. So how we can make 8 atoms of hydrogen over here? We will put a coefficient 4. 4 into 2 is 8. So our hydrogen is also balanced. So it's a perfectly balanced equation. So always remember, try keeping hydrogen oxygen in the end so that we can balance the other thing. The other thing over here is only iron. So it was a simple equation. Next that we are going to discuss is we are going to summarize the information conveyed by a chemical equation. So we have already discussed many points, but we are going to summarize it. So first thing is the ratio of moles of reactants and products. So if you go back to this equation, so I can write like this: 3 mole of iron, the same coefficient, reacts with 4 mole of steam to give us 1 mole of triiron tetroxide and 4 mole of water. We can do this. So the coefficients are nothing but the number of moles. Then ratio of masses of reactants and products. So how to prove this one? So let's go back to this equation, Haber's process. So nitrogen mass is 14. In the previous lectures we have discussed. So 14 into 2, this gram atomic mass will be 20, gram molecular mass will be 28 gram. So hydrogen 1 mass is there. So 1 into 2 into 3, so this will be 6 gram. And ammonia, if we need to calculate, so this will be 14 plus 1 into 3, and this whole multiplied by 2. So this will be 34 gram. So this weight, that mass, ratio of masses of reactants and products after balancing the equation is going to be constant. It's not going to change. It's not going to change for nitrogen, it's going to be same. It's not going to change for hydrogen, so it's going to be same. Then relative number of atoms and molecules of the products formed in the reaction. Similarly, we can write the same statement of reactants also. So for reactants and products both, relative number, the actual number that we are talking about. Then we can write formula, symbol, names, physical states of reactants and products. Then one more we can add. For this again we are going to use a Haber's process equation. Ratio of the volumes of the gaseous reactants and products. So how we can prove this one? So again I am going to take one equation for this. Same equation, Haber's process. So we'll balance it later. So this is in the gaseous state. So they said ratio of the volumes of the gaseous reactants and products. So this is something we call it as Gay-Lussac's law. So it says the stoichiometric, whatever you want to pronounce, the stoichiometric coefficients can be taken as simple whole number volume ratio provided the reactants and the products are in the gaseous state. So this reactants and products are definitely in the gaseous state over here. So we are going to put the coefficients the way we did before. We are going to balance this equation. So 2 over here, 3 over here. So this is perfectly balanced. So we can say since nitrogen and hydrogen is a gas and ammonia is also in the gaseous state, so we can say one volume, since there is no coefficient over here, so we'll take it as 1. So 1 volume of nitrogen reacts with 3 volume of hydrogen to give 2 volume of ammonia. So this is very simple, a simple question that you can get, that what is the simple whole number or volume formed, like one volume of nitrogen reacts with 3 volume of hydrogen. So what volume of ammonia is formed? So in that case you just have to balance the chemical equation so that you can get the number which we are going to take it as simple whole number volume ratio. Then after that we can discuss about advantages of writing chemical equation. So why we write chemical equation? Why we can't write in the word format? So why it is essential, or why it is very much advantageous for us? So the advantage that we can use over here, the representation of actual chemical reaction becomes easy. So it saves a lot of time and space in writing. Effect of temperature, pressure, and concentration on the rate of reaction can be investigated with the help of perfectly balanced equation. So that can be one advantage. Then it's easy for chemists to understand, be it any country. So if we write this equation, if I am writing this equation for any chemist to understand, for any chemistry teacher to understand, it's quite easy to understand that nitrogen and hydrogen is combining in what ratio. Now this can be mole ratio also, 1 mole reacting with 3 mole of hydrogen to give 2 mole of ammonia. So the ratios can be calculated easily. That can be one thing. So I'm not writing, but I just explained it. Then limitations, or so better word, limitations, not disadvantages. Limitations of a chemical equation. So chemical equation does not indicate about the rate of chemical reaction or time taken for the completion of reaction. Then it does not indicate whether the reaction is explosive or not. So some reactions are explosive that cannot be revealed by a chemical equation. So how we can find that out? We can only do that in the lab. So just by writing equation, you cannot predict whether the reaction is taking place at high temperature, low temperature. So those are all experimental data that we write along with the equations. We write above or below the arrow. So that's how we indicate it. So we have to memorize it. But practically done the same equation, at least you will have a fair memory that how that reaction proceeded. So if we don't know what is the experimental uh, investigation of a chemical reaction, we can't write it in a book, we can't even publish that. So we have to write in the theory, we have to write in the literature that this chemical equation is very much explosive. So if we don't, then we might not know about that chemical reaction, and you might end up doing the chemical reaction in the lab and without having any idea whether it's explosive or not. So we need to keep all these precautions. So that is not revealed by chemical equation. Just by writing chemical equation, we can't do that. We can't predict that. So chemical equation, the third point, does not tell us about the actual quantity of reactants consumed or products formed. It only gives us about indicates us about the molar ratio. It's going to give us the standard weights. It's never going to, it only indicates about the molar ratio over here if you see. It's not going to indicate the amount, the actual amount the industries are going to use. So chemical equation is very useful to calculate the amount of all of the substances consumed or formed. If the amount of these, anything, if amount of these is known. If it is not known, then we can't calculate it, the actual amount.